In this lesson, we're going to look at probability tables. So before we do that, I want to talk about two different formulas. So the first one here is the conditional probability formula, which really means a given. So if you have the probability of A given B, so remember this little bar here means given. So what this is saying is the probability of A happening given that B happens. So this means the denominator or your possibilities has to be event B, or the probability that B happens, since it's given that B happens. And then up top, well, B has to happen as well as A, because it's the probability of A given that B happens. So we represent that as the probability of A and probability of B. So notice this symbol right here. This represents and. It's the intersection, so it means that both things happen. And then this symbol you've seen before with interval notation. This is the union. This is the or, so one or the other. So if you see those symbols, that's what it means. So that means when we go into this or formula, so the probability of event A or event B. So here's the or. This is, remember, or means addition, so it's the probability of A plus the probability of B, but we have to remember that if there's any duplicates or any overlap, we have to subtract those off. So what that means is if there's anything in common between A and B, we subtract it. So this is what's in common would be the probability of A and B. So that would be your duplicates. So that's what the formula looks like. So let's go ahead and let's look at this first example here. So we have a chart. So it talks about a local company interested in supporting environmentally friendly initiatives such as carpooling among employees. The company surveyed all of the 200 employees at the downtown offices. Employees responded as to whether or not they own a car and to the location of the home where they live. So here's the results. So just to kind of interpret the table here, we have our columns. It's talking about the location of their home. And then we have our rows, which is talking about car ownership. Notice the 200 employees is right down here in the corner. So the total number um, of the car ownership. So we have 60 people that own a car, 140 that don't. When you add those together, that gives us the 200. And then 70 people in the downtown area, 70 people elsewhere in the city, 60 people outside of the city. Add those up, and that talks about the 200 people. So that's kind of how you interpret. Versus like if I'm right here, 10 would represent people that have a car and they're in the downtown area. So that's how you interpret the table. This is called a two-way table because there's two different scenarios that we're comparing. So two-way table or two-way frequency table is sometimes what it's referred to. So then if we actually look at some examples, what is the probability that an employee owns a car? So the probability that an employee owns a car, so this is just any employee. So out of the 200 people, how many of them own a car? So car ownership, yes, go all the way to the end of the row. That tells us that there's 60. So this is considered a row probability because the total is coming from a row. And I'm just going to leave this. I'm not going to worry about reducing this. What is the probability that an employee lives in the downtown area in the city? So employee lives in the downtown area. Well, downtown area, there's 70 employees that live in downtown out of the total number of employees. So this would be considered a column probability because the total is coming from, or it's coming from a column total. This one says, what is the probability that a person owns a car? So owns a car and lives in the downtown area. So for this, whenever you see an and, it means that you need both of these things to happen. It means that you're looking for the intersection. So we're looking for the intersection of the row and column. So you are looking, you don't really need to do a formula for this because we're talking about, okay, well, out of the 200 people. So let me go ahead and put that. So out of the 200 people, we need the person to own a car. So I'm going to use my highlighters here to kind of show you. So own a car. So here's all the people that own a car. And we need them to also live in the downtown area. So downtown area is this, and we can see where that is happening, where we have the intersection or what's in common is going to be 10. There's 10 people that live downtown and own a car. So that's it. You don't need a formula for that. Remember we talked about and before meaning multiplication. In this situation, you're just looking at the intersection in the table because you can see right in the table where it's happening. So now we look at the next one. What is the probability that a person owns a car? Or, so now we think or means addition, or it means that we're using our formula here. So this means you're going to use your formula. We have to be careful about using the rules of addition versus multiplication because we're going to learn about it in the next lesson about independence. So for now, just know when you have a table and it's and, use both, use the intersection. And if it's an or, that's when you're going to use the formula from up top. So what I'm going to do for the formula, so let me just write it. So the probability of A or B is going to be the probability of A plus the probability of B minus the intersection. Oops. So what this means is I need to know the probability. So if I call this event A and this event B, well, the probability that a person owns a car, so we already have that right here, but let's pretend we don't. So owns a car is 60 out of 200. So it'll be 60 out of 200 plus downtown area. So 70 out of 200 minus the and or the overlap, which is what I just found in part C. So 10 over 200. And then we actually go ahead and add and then subtract, and we get 120 over 200. So we have the probability of the person owning the car and living downtown, but then we have to make sure that we subtract off the 10 people that are doing both of those because really within the 60 and the 70, you're counting those 10 people in each of those. That's why you have to take it away. So you're taking away the duplicates, which again is really just using this formula. So that's and versus or in the table. The other scenarios are the given, so using that conditional probability. So for this one, it says, given that a person lives outside of the city, what is the probability that they own a car? So a lot of times the givens are going to come at the beginning of the sentence, not always, but in a lot of times they will. So this is your denominator. This is what you have to have. So this is basically saying the probability that the person owns a car given that they live outside of the city. So that means we need to know out of all the people that live outside of the city, so all the people that live outside of the city, there's 60 people that live outside of the 60. So out of those 60, how many of them also own a car? So this means there's 35 that live outside of the city and own a car. So that's the intersection of owning a car and living outside of the city, given that they live outside of the city. So this is going to be 35 out of 60. So essentially, this is own and outside out of the people that live outside, if you kind of compare that to the formula up top. All right, so let's go to the next page and let's actually do another problem with a table. So just so you're aware too, sometimes the tables aren't going to be filled in completely for you. So if you had to fill in a table, which you will in the homework, all that means is, remember, your row totals have to add up to whatever numbers at the end. So all of these numbers have to add up to the end of the row, and all the columns have to end up to the numbers at the bottom of the column. And the all of the totals in this column and all of the totals in this row have to add up to this number at the end. So that's kind of how it all ties in. It should make sense when you're looking at it. So let's go ahead. So we have this survey that asked 1,005 US adults. So again, notice that number here matches total number of adults surveyed, total number, um, who think who think they who they think, there we go, who they think better fits their idea who should be president. So this is an older survey, but we have what is the probability that they thought Trump should be president? So let's go ahead. So this is out of our people that were surveyed. What is the probability that they thought that Trump? So out of the 1,005 people, how many of them thought Trump? Well, we go to the Trump total, so all age groups here. We had 518. And that's it. I'll just leave it like that. Next one, what is the probability that the person is in the 50 to 64 age group? So again, out of all the people, what's the probability they're 50 to 64? So go to 50 to 64. There's 205 people. The next one here says, what is the probability that they are in the 50 to 60 age group? And so this means both have to be true. We're looking for the intersection. They think Trump should be president. So 50 to 60 age group. So we're looking here, 50 to 64 age group. And Trump being president means that there's 112 that satisfy both this column and this row. So 112 out of the total number of people surveyed. The next one, what is the probability that they are in the 50 to 64 age group? Or, so this means formula, they think Trump should be president. So basically, we have those probabilities. All three probabilities that we need are in A, B, and C. That won't always be the case, just so you're aware, but it is for these problems. So what is the probability that they're in the 50 to 64 age group? So that's my answer for part B. So 205. Or, so I'm going to add Trump should be president. So that's 518 over the 1,005. Now I have to subtract off the people that are in both categories. So I need to subtract off the duplicates. So there's 112 people that are in both categories. So I have to subtract them off because otherwise they're counted twice. So again, remember this is the duplicates that we're subtracting off. Now notice I didn't write out the formula for these. You don't have to write out the formula. I know normally we say write out the formula, show your substitution, but I feel like for this you can kind of just think through it without writing and using the formula. So if you prefer to just memorize the formula and plug in, then write the formula and plug in. But if you're just kind of thinking through it, then this is totally fine. This is enough work, just so you're aware. So then now when I do the math here, 205 plus 518 and then minus the 112, I get 611 over the 1005. Now we have some givens, so some conditional probabilities. So given that the person picked Clinton, what is the probability that they are 18 to 29 years old? So what we need to have here is given that they picked Clinton, what's the probability that they still have Clinton and are 18 to 29 years old? That's really what we're looking for. So out of the people that picked Clinton, so let me just scroll up. So there's 437 people that picked Clinton. What's the probability that those people were also 18 to 29 years old? So there's 135 out of the 437. So again, you don't necessarily have to show this written work here. This is just me kind of showing you how the formula is being used, but you can really just kind of think through it and go right to the numbers. That's enough work for that. A couple more. So given that the person is 18 to 29, so now we're looking at basically the flip. What's the probability that they chose Clinton? So given that they are, so how this one changes is now the 18 to 29 years is on the bottom. So given that they're 18 and 29 years old, what's the probability that they picked Clinton and are 18 to 29 years old? So the numerator is going to be the same because there's 135 people that picked Clinton and are 18 to 29 years old, but the given is different. So now what we're looking at is out of all the people that are 18 and 29, so out of the 217 people, how many picked Clinton? Well, 135 out of the 217. So 135 out of the 217. So you can kind of compare those probabilities between the two different situations. One is definitely more likely to happen. So given that the person's 18 to 29 years old, they're more likely to pick Clinton versus the people that pick Clinton are less likely, I would say, to be 18 to 29 because this is a smaller percentage compared to the 135 out of 217. So that's kind of how those two different scenarios compare. And then lastly, we have if the person picked Trump. So this is a given. Notice that it doesn't say given, but it's the same meaning. So it says if the person. So this kind of indicates given that the person picked Trump, what is the probability that they are over 65? So again, given that they picked Trump, what's the probability that they picked Trump and are 65 or over 65? So let's go ahead and look in the table. So given that they picked Trump, so 518, what's the probability that they're over 65? 92 out of 518. And that's it. So that's using the tables to figure out probability. It's pretty much the same thing over and over. There's not really a whole lot of um, trick to it. It's pretty straightforward. So just remember, and means look for the intersection, or means use the formula, and then your givens, you can use the given formula for those. So go ahead and do the homework problems.